In this section, we're going to be finding area under a curve. And example 1 is going to help illustrate why we care about finding the area of a curve. Example 1 says, let's say that you go to the gas station and are filling up your car with gas. If gas costs $3 per gallon and you fill up your car with 10 gallons of gasoline, how much money will you have spent? Now you might be asking yourself, what does this have to do with area under a graph? Couldn't we just figure out this problem using algebra? And you're absolutely right. We can. So if we have $3 per gallon, and we multiply that by 10 gallons, the gallons will cancel out, and 10 times 3 is $30. So you will have spent $30. Now, another way of thinking about this is we can create a function that will generate the cost for us, or the cost function. And so I'm going to call it f of x is equal to 3x, where f of x represents total cost, and x, our input, will be number of gallons of gasoline. And so now, you can plug in any value for x, and we'll get the total cost as the output of that function. And if we were to take the derivative of that function, the derivative is a constant. And so that's the rate at which the cost is changing. And it turns out that if you graph the derivative function, which it's just going to be a horizontal line here at x equals 3. And if we if we examine the area under the curve between x equals 0 and x equals 10, this shape here that's formed is a rectangle, right? And so this length here is 10, and this length here is 3. So the area of that rectangle is 3 times 10, which is 30. And that also helps us to figure out the total cost. So this is kind of the motivation in this section of why we want to be thinking about the area under curves. Now, in a lot of scenarios, it's not going to be as simple as it was in this example, because if we are looking from A to B underneath this curve, this shape here is not a rectangle, so it's not as simple to find the area of that shape where it was here because we had a rectangle. But again, this shape here is not a rectangle, so it's not quite so simple to think about in terms of the area. So we're going to have to use different techniques. Example 2 says estimate the area between the function y equals 2x and the x-axis from x equals 0 to x equals 1. Now, this is another example where here we're being asked to estimate the area, but we can actually find the exact area because of geometry. So if you're looking at the shape that is formed by the line y equals 2x and the x-axis, this shape here, it forms a right triangle. And the area of a right triangle is equal to 1/2 the base times the height. And in this scenario, let's see, so we know this length here on the bottom is 1, and then we know that this length here is 2. So the area is going to be 1/2 times 1 times 2, which is going to equal 1. So the exact area under the curve for this example is 1, but we are still being asked to approximate the area. And one way that you can approximate the area is by using rectangles. So the idea is we're creating rectangles underneath the curve so that because we know the area of a rectangle is equal to the base times the height. So if we took the area of each of these rectangles, if we calculated these areas and then added them all up, that would give us an approximation for the area underneath the curve. Now, hopefully you realize that all of these rectangles go above the actual line. So if we were to add up all of these areas together, our approximation is going to be over the actual area. So it's going to be an over approximation. So just keep that in mind as we are thinking about these rectangles. So I've kind of made some columns here so that we can fill out a little table to help us figure out the areas of these rectangles. Now, one thing to notice is that this is x sub n, so we don't quite know how many rectangles there are, but the way that we're going to fill out this table is we'll figure out the information for the first rectangle, the second rectangle, the third rectangle, and then all the way down to the nth rectangle. And another thing to notice is the way that's going to make it easier for us is if we make sure that all of these rectangles have the same base length. And the way that we do that is if we have n of them, then basically we're just going to take 1 and divide it by n. So let me give you a more concrete examples. If we decided that there were 10 rectangles, then each of the rectangles would have a length or a base length of 1 over n, which is 10. So each of these would have 1/10, 1/10, 1/10, and then they would have different heights. But that was just an example if n were equal 10, but we don't know what n is. So the base length is going to be 1 over n, and it's actually going to be, like I said, 1 over n for all of these. And then the right endpoint for the first rectangle is this value here, x1. So I'm going to call it x1, which is equal to 1 over n. And then the height is going to be f of x1. And we know that our function here, we could, f of x is equal to 2x. So if this is x1 and it's equal to 1 over n, then the height of this rectangle here is going to be 2 times 1 over n. And then the area of that rectangle that I highlighted here is going to be the base, which is 1 over n, times the height, which is 2 over n. So it's going to be 2 over n squared. Okay, let's fill out more of the table. So x2 is going to be this point here on our graph, and that's going to be 2 over n. So f of x2 will be 2 times 2 over n, and then the area of the rectangle will be 1 over n times 4 over n, which will be 4 over n squared. Then x3 will be 3 over n, and f of x3 is going to be 2 times 3 over n, and then the area of the rectangle will be 1 over n times 6 over n, so that will be 6 over n squared. And hopefully you're seeing a pattern here that's happening. So x sub n would be n over n, and then f of x sub n will be 2 times n over n, and then the area of the rectangle will be 1 over n times 2n over n, and then that's going to equal 2n over n squared. So the approximation for the area now, I'm just going to call the area A, is going to be approximately equal to 2 over n squared plus 4 over n squared plus 6 over n squared plus ... to the 2n over n squared, that last term here. And each of these terms are representing the area of one of those rectangles.